Hello everyone, this is S.V. Jason. I am here to present my presentation on FERMI-ML, a flexible and resource-efficient memory-in-situ SRAM macro for TinyML acceleration. So here are the authors. Mukul Lokande works as a research scholar at Department of Electrical Engineering, IIT Indore. Akash Sankhe is currently pursuing his master's at Nanoscale Devices Group at IIT Indore. I am S.V. Jaychand. I am pursuing my Bachelor's of Technology in Electrical Engineering, IIT Indore. Shivangi Mishra is pursuing her PhD at Electrical Engineering, and Dr. Santosh Kumar Vishwakarma is a professor in Department of Electrical Engineering at IIT Indore. So coming to the outline, we are going to discuss the following things: introduction and motivation, the proposed work, which conscribes of 90 XNOR-based SRAM bitcell, a 22T based 4x2 compressor, digital computing memory architecture, and a performance comparison with the previous state of art SRAM cells. And we will conclude the session. So introduction. Coming to the introduction, so as we all know, the modern day IoT technology devices require a lot of memory and billions of MAC operations and hundreds of millions of parameters. So it stresses on compute and memory resources. Although the technologies go on efficient, the major problem is one human bottleneck. So the energy and latency are dominated by data movement between memory and compute these days. So, for example, the famous VGG16 model for image classification has 138 million weights, so leading to significant memory access overhead. So, in order to mitigate this, we are proposing a memory in situ PIM model. So, in in order to stop the movement excess movement from memory to computation area, so we introduce a simple logic inside the memory array to avoid costly transfers. So although there are few existing works like in both analog and PIM and digital PIM categories, there are some problems with those, with especially with digital PM, there are less fixed constrained accuracy and precision. So most of the existing models are in 4-bit precision. So in order, we are trying to mitigate that. So our motivation is mainly to reduce usable cache area and limit precision. So as the previous 60 or 80 cells and extra logic, they require a lot of cache area. So we need a PIM architecture that provides high storage density, energy efficient accumulation, flexible precision computing, and multi-mode use, both using PIM and CAM capable cell. So we have proposed the following cell. So it's a 90 XNOR SRAM bit cell. So the bit cell looks as shown in the left. So it has 5 transistors mainly for memory storage and 4 transistors for XNOR computations. And based on the row and column activations, we can read it two sides, and there is a writing capability in it. It stores the data, and also there is a multiplication capability, and we can also address the memory using content. So here are the results, is how it shows. So the power and read delay comparison are shown. So it works quite well when compared to the previous state-of-the-art models. So and also area and write energy comparison is also shown. It is significantly better in terms of write energy too. So we have also checked the performance of our bit cell at different conditions. So here we can see that based on the supply voltage, the performance of the SRAM bit cell for CAM operation using LUTs, and the same can be seen on the right side for the performance in matrix multiplication of processing and memory computations. So here are the bit cell operation. Here is how the table looks. So at different conditions, these are the lines that need to be manipulated using control logic, and the resulting results will be shown. So the types of operation are shown here. So there majorly it is of content addressable memory and processing in memory. Inside content addressable memory, there are two ways. So binary mode and also ternary mode. Binary mode, each 90 bit cell is a single pcam. So it only is capable of addressing 0 and 1 states. So ternary mode addresses an uncertain x state on top of the both 0 and 1 states. So what it uses two bcams. Each bcam refers to a single state. Based on if both are zeros, the resulting mode is 0. If both are ones, the resulting mode is 1. If both of them are different, so the resulting mode is an uncertain state x. So coming to the processing in memory mode, so we have used a reconfigurable sense amplifier at the bottom of the array. So using that, we can use it as two single-ended essays, sense amplifiers. So by referencing the voltage below 100 millivolts below VDD, we are able to use that and perform matrix multiplications. So by activating multiple roles simultaneously, we can perform multiple operations directly inside the memory. So coming to the next stage, the proposed 22 transistor based 4x2 compressor. So we all know that compressor based accumulation and logarithmic parallel shifters are an integral part and take a lot of resource. So in order to mitigate that and reduce the transistor count compared to previous models which have around 40 transistors, we have proposed a 22 transistor model. So it is made up of two stages. The stage 1 is of pass transistor logic and second stage is of CMOS logic. In pass transistor logic, we reduce the count of the transistor and also the cell delay and power is also reduced. It produces high speed result in terms of carry, but it has a little problem regarding noise immunity and signal restoration. So the second stage compensates that. The CMOS stage has better drive strength, better noise immunity, and it produces a strong sum output, and it's pretty error tolerant. So understanding the results, it has a 2.23% error rate and an NMED of 0.38 and a mean magnitude error of 0.256 for 8-bit accumulators, which is quite well for TinyML models and for approximate computing. Coming to the final proposed digital compute in memory architecture. So the architecture supports 1 to 64-bit precisions. It also supports a POSIT 4 and FP4 using content addressable memory. So each bit cell is of each macro is of 4 KB. So it computes 4096 1-bit operations, 1024 2-byte operations, or 256 in 4 operations and 4 in 32 operations if used in parallel. So comparatively, they are 1.2 times faster, 92 times faster than the previous state-of-the-art models, and 1.28 times more power efficient. So, in essence, its effective storage density is 240 KB in place of a 1 MB cache. So we have also in order to compare to the state-of-art models of which are of around 16 KB, we have used the 4 KB macros and connected them quite well and be able to compare and compute. So the performance comparison wise, because of the multiple input width and weight width variations and also capabilities of multiple precisions, we are also able to get a pretty good accuracy of 95.6%, which is quite good for approximate computing in image detections, and a tops throughput of 1.93 and the tops for watt efficiency of 364. We have worked this in 65 nanometer technology node with a varying supply voltage from 0.8 to 1.2 volts with a frequency of 450 megahertz. So it is significantly fast with 1.28 times faster than the state-of-the-art RD scheme design. So in order to compare, we have scaled it to 16 kilobit. So concluding, This work introduced the flexible resource efficient memory in situ SRAM macro using our developed 90 XNOR bitcell and C22T compressor tree, enabling scalable low power precision reconfigurable MAC and CAP operations inside the same circuitry. And with a high tops and energy efficient, this model is also having a pretty good accuracy at 97.5%, outperforming few digital PIM designs. So with a unified architecture, it supports the LUT-based nonlinear activations, enabling efficient computation of functions which are complicated like sigmoid, tanh, and softmax function within the same macro. So the future extensions we target are multi-bank parallelism and risk-free socket integration, positioning the macro as a high-density L3 cache for on-chip TinyML learning. Thank you. Thank you. And please suggest and get your questions answered at the following email IDs. Thank you.